I just want to quickly go through the slides. I won't spend much time, but we'll just quickly go through the slides and then where we stopped yesterday. Okay, I'm going to reiterate some of the stuff, but most things is new for you. So what we see here is a battery in the pluses here, and the diode anode is there. So when the anode is connected to the battery plus, we call this forward biasing. Battery plus to the anode. However, when you swap this diode around, in other words, now then battery negative is touching the anode, we call this reverse biasing. This reverse biasing is quadrant 3. The forward biasing is quadrant 1 of your graphs. So you can see on this diode that the anode is on this side here. It's the plus side of the diode. And the cathode is the minus side of the diode. And I always remember it with this minus here connecting to the little arrow line here. That line is a minus, you see. So that's how we know that's a minus of the power supply. And the plus of the power supply is the anode. So just remember that. All right, so when current flows in this direction through the diode, it is forward biased. Okay. However, when current tries to flow in this direction, it's reverse biased. So in forward biased, it's always the normal current through the diode, but in reverse biasing, the current is very small, much smaller than forward biasing. The diode cannot take a lot of current during reverse biasing. Only a few, like microamperes. The only diodes that work with reverse biasing actually is zener diodes. And a few others, we'll get to them. The next slide. It just tells you about conductors and insulators. Insulators are like plastic, rubber, glass, wood, and cloth. They are insulators. Except if you put the wood maybe in water or salt water, it will be somewhat conductive. Your conductors are always metals. So copper is a metal, aluminium, steel, gold, and silver. They are all metals and they are good conductors. I'm just reiterating this. I know we've done it before. So the diode works like this. There's a band gap here, and the band gap gets smaller and smaller as we put more voltage or less voltage on the diode. So we can increase the band gap region with that. Okay. The band gap is the amount of energy that the electrons must have to jump from the valence band to the conduction band. In other words, to conduct the current. You're going to read these slides also. I'm not going to go deep into them. N-type materials. These are sort of, N-type can be created by creating 5 elements in a periodic table. Only those 5 elements will work as semiconductors. And we dope it with a material, so we can use silicon or germanium. And we can dope them with arsenic, antimony, or phosphorus, but usually arsenic these days. But we dope it and we make it slightly conductive in one direction, and now we call this a semiconductor. This circuit, I just want to explain the little circuit to you. This is for practical diode circuit. For a practical circuit to work, we can connect a battery to a diode. But remember, there's a problem. The diode voltage is 0.7 usually, so VD is 0.7 volt. Except for germanium where it is 0.3 volt. And for LEDs, it's usually about 1.8 volt or 2 volt or so, this voltage. So when we don't have a resistor in our circuit and we just put the diode over the battery, the current will be so large that the diode will blow. For instance, if the diode resistance, inside the diode, there's always a little resistor, but it's very small. It's usually like 0.1 ohm, some are a little bit more, some are a bit less. But so if I put a current through this without a limiting resistor, my current will go over 100 amps. And I will blow the LED. I will blow the circuit in the diode. So I can't do that. I must limit it with a limiting resistor. The current limiting resistor we put in series so that some of the volt drop can be falling over this resistor and thereby limiting the current to a small value so that we don't blow or burn out this diode. In your experiments, Ian, you've seen when you put a diode directly across a power supply like that, you can blow the power supply. You will also blow the LED because the current taking by the LED is just too much for the power supply to supply. And you can damage the power supply too. So the current limiting resistor in this case will limit that current. So what will my total resistance be? 100 ohm. That 100 ohm plus the 0.7 resistance here. You see that resistor is built into the diode, 0.1 ohm. So my total resistance for this circuit will be 100.1 ohm. My total current flowing here will be limited to 10 volt. Divided by 100.1 ohm, that's 99 milliamp. And in this way, we actually limit the current. So a non-practical circuit won't have any resistance, but a practical real-life circuit will have a resistor there to protect the thing and so that this circuit cannot blow up the power supply or the diode. Okay, I'm done with this slide and I want to put up my next set of slides. Are there any questions on this, people? Do you have any questions on the circuit and how to use a diode with a resistor?
Yes, sir, there's a question.
Yes.
So, sir, you said the resistance on the LED, is it always 0.1 or it depends if it's silicon or germanium?
What do you mean, the resistance inside the LED or what?
Yes, sir, the resistance inside the diode. So is it always 0.1 or does it depend?
Okay, that's an interesting question. Good that you're asking. Look, an LED can usually only do 50 milliamp. Okay, and the voltage over an LED is about 2 volt. So you can quickly calculate that resistance of the LED, right? Because it's 50 milliamp is the highest current can go through an LED, except for very special LEDs that's nowadays bigger. But I'm talking about the normal small LEDs that we know. So it's 2 volt divided by 0.05. So that resistance is for a LED is about 40 ohm. Okay. So it depends on the diode, and every diode will be different. And this value you can find it in the data sheet of that LED or other diode. Okay. The data sheet will tell you its internal resistance. Okay. But there is a little resistor in, but it's very small. Sometimes it's less than 1 ohm. Does that make sense?
Okay, thank you, sir. Yes, sir. Thank you, sir.
Just stop sharing this. Put another set of slides on. Right, so just gotta find it. It takes a bit of a while with this online class. Is not very good. It's always slow to do online classes. I don't love it. I really don't want to do it. Right, guys. This is now part 2 of the slides. So again, I just want to show you that the diode, when it's forward biased and reverse biased. So we've got these two diodes. This is the anode on the triangular side, and the minus is that stripe there. You see that stripe? That's your minus. Let me use my laser pointer. That stripe there is the minus or the cathode. This is in this case for a zener diode. See the two little extra lines there that shows you this is a zener diode. So for a normal diode, it's forward biased in this region where the battery plus is connected to the anode here. And for this region, the battery plus is connected to this one. So battery minus is connected to the negative side of the cathode. In that case, this diode is forward biased and the graph will be in this quadrant 1 of your graphs. However, when it's reverse biased, I will connect in this for this quadrant 3. I will connect a minus to this anode side, the minus of the battery to this anode side. The plus of the battery, I will connect to this negative side, which is the cathode. All right. Now, in this case, the diode will be reverse biased and there will be a reverse current flowing. And that current will be on this axis, so it's minus, say, 100 microamp. And the voltage, the reverse voltage over it will be, say, minus 10 volt here in this case. So about minus 10 will be about here. So that means it's reverse biased in this region. So when you look at one of your questions there in your the questions that if you in the tutorial, this is one of the questions. Okay. So a zener diode basically can work only in reverse biasing. Now look in this funny case. The diode is upside down. So the positive of the battery goes through a resistor to limit the current. Remember I said we must limit the current. Now, to limit the current to say half an ampere, we must put a resistor here big enough. And so the plus of the battery goes to the cathode of the diode, which is totally wrong. It means it is now reverse biased. And this zener diode wants to work like this. It's one of the only diodes that works in reverse bias mode, except for the variac diode also. So the anode of the diode goes now to the negative of the battery. And this shows you that it's reverse biased. Okay, so zener diodes operate in reverse bias. They come in a range of voltages. The zener diodes, I've got these zener diodes here at my house. They work from about 2.9 volts for the small one, and then about 4 volt. The next value is about 4.5, and then it's 5.1 volts. And then it's about 6.2 volt and 7.5 volt, and you get it in all the voltages up to about 100 volt. So when you buy it at the shop, you must ask for the right voltage for the zener diode. And the voltage of the zener diode will determine what voltage will be sitting here, which you measure with your multimeter. If you buy a 5.1 volt zener diode, and you put 12 volt in here, it will make sure you only get 5.1 volts out here. you buy a 9-volt zener diode, you put your 9-volt zener diode there, you put 12 volt in here, and what will you get out? Also 9 volt. So the beauty of this zener diode is it will always regulate the voltage. We call it regulation. It will regulate the voltage to be a fixed zener voltage there. Okay. So in forward biases, the zener diode, if you turn it around here now, in forward bias with its anode to the top and its cathode to the bottom, if you do that, then this zener diode will also have 0.7 volt drop over it. In the forward bias, it's got 0.7 volt. In the reverse bias, it's got the zener diode value, which is in this case 5.1 volt. Right. Now, we've done this to the slide. This is varactor diode. This varactor diode also works in a reverse bias. And I want to show you that when you've got no power supply, there's no power voltage here, and you put it over the diode, then this depletion region is very narrow and it won't conduct any current. However, when you put a larger voltage over here, it will start conducting current because now the depletion region went wider because of the voltage. I've done this really, the capacitance will also now increase with the depletion region. And here you can see the graph. The higher the voltage, the smaller the capacitor value. So the highest voltage here is about 30 volt. Capacitor value will be about 4 picofarad. However, about 1 volt here over it, the capacitance value will be 40 picofarad. So it's inversely proportional to the voltage. This diode is special. The varactor diode is also working in the reverse bias. It tells you here in the reverse bias. I've done this circuit really, people. You can look at the slides on Brightspace again. But this is just how we can use a varactor diode to change the capacitance so that we can change the frequency of a circuit here. And so we can control frequency with that by changing this value of the capacitance inside the diode. This diode is drawn like that. A triangle, which is the anode, and a cathode is 2 capacitor lines. It's all built into the diode package. You can buy them for about, I've got some, you buy them for about 25 rand each. They're not so expensive. LED, we really know the LED, and we know that the plus is the anode here. You connect that to your plus of your battery, and your cathode, it's got a little flat spot here. It tells you the cathode of an LED. That's how we know which is a cathode. Some people say the one leg is longer. I never trust that because that's not always the case. Never use that. Always use this flat spot on the side of the LED that tells you that's the cathode side, the minus side. Right, I've already shown you this circuit, the current limiting resistor, and it will limit the current going through that LED. So different LEDs have different forward voltages. I just want to show you that again. A red LED forward voltage, that's about, on the graph here, you see there, 1.8 volts roughly. A green LED, that is about, in this case, about 2.2 volts. And a blue LED is very high, people. It's about 2.5 volts. So different color LEDs, it's different forward voltages over it. But LED is the only LED with a higher forward voltage than other diodes. All the other diodes, forward voltage is 0.7 volt. Also, as the current increases, in this case, the current increases, the voltage over the LED will also increase. And it will show you That's also green, blue, and red LEDs. For different currents, it also gives you different values of light coming out of the LED. This is a 7-segment display where we put LEDs in a form of segments and we can light them up and making any letter or character. 7-segment display and how we connect it up through resistors. These resistors protect the LEDs from not blowing. If we remove those resistors, all these LEDs will blow up. Right. We can also use 2 LEDs back to back like this. We put plus here and minus there. The red LED will glow. However, if we put plus on this side and minus on that side, the green LED will glow. Again, here we can use 2 colors, and this is a tricolor LED. We could red and then green, and when we put both on, it'll be sort of a green bluish light. Call it a tricolor LED. Okay, another one that's an optical diode. The optical diode, you can shine light on it here with a laser pointer, and it will tell you when the current flows, the light is on. And it's a magic way to send information from a laser to on one end of a fiber optic to the other end of the fiber optic and put data in from the laser, and you can receive the data where the optical diode is. This optical diode is always used in the reverse biased as well. And this is also one of the reverse bias diodes. I'm not going to go much on and off here. It just shows you when you shine light and you don't shine light. When there's no light, there's no current flowing here. However, when I shine light here, it becomes conductive and the current will start flowing through it. And that's how we can switch it off and on with light. You can shine a LED light on it, or you can shine a laser light on it, or just a normal car globe or a light globe. You can shine light on it, or the sun. The sun shines on it, it will start conducting current. Right. This is a current regulator diode. It's a constant current. It will control the current through the LED or through the circuit. The Schottky diode. Schottky diode, not much is different from a normal diode. It's always in a forward bias. And a Schottky diode voltage is lower. It's about 0.3 volts. Schottky diode has got a little thing there. It looks like an S, so that's how you can remember it's a S for Schottky. That little curly looks like an S. It's a very fast diode and it's used for high frequency applications. You can read it here. The questions sometimes in the test come out of these notes here on the side. So you guys must learn and read through this. Okay, a pin diode is another type of diode. And this is a reversed bias pin diode and a forward bias. In a forward bias, there's a changing resistance on it. But in reverse bias, there's a changing capacitance will change on it there. Tunnel diode, guys, you can read through this. Sometimes this question is in a question paper, so don't forget it, read about this. I already done it yesterday. It's got a negative resistance, you can remember that. And what else can I say about it? It's a negative resistance. And in forward bias, it will conduct well. This is just a tunnel diode oscillator. We can build an oscillator with it if you put a diode like that. And with the RC value, it will start oscillating. It will give out a sine wave, a frequency like this. So we can use it for a frequency generator, a sine wave generator. That's what they do with it, tunnel diode. The laser diode, it's got a P and an N part, so the anode on top and cathode here. And the laser will actually give off light on the side. We call it the edge emitter laser diode. And on the edge here, there's a white gap here, or split there. And it will give out light from here to there, about 2 millimeter width. So it's a flat sheet of light coming out of the laser diode. To make the light round, they usually put it through a lens, and the lens is in front here. There is a lens in front of the diode. That's how they do it. You can read this stuff through as well. I'm done with these questions. Stop sharing, and then I put the third one in. All right, so my next slide is the next set of slides. I will quickly go through that as well, and then we can do the tutorial that I actually want to get to and start doing that. Sorry, it takes a while to load. Right. Right, guys, this is the slides that we already went through. So just quickly, I'm going to go through it quickly. And semiconductor theory is, we can just discuss the stuff. I'm going to skip all the covalent bonding and all those things. I just want to get to the nitty-gritty. I've showed you the forward bias diode circuit, and this is how it looks. And the reverse bias is when the current goes in this direction, reverse biasing this diode. So we know that only a zener diode works reverse bias, a varactor diode, a pin diode, and what else is it? Only those special diodes really work in the reverse biasing. Oh, and the optical diode also works with this reverse biasing. I'm going to skip about the cell, the atomic structure in this stuff. I've done it yesterday. We're going to skip that. We're not doing that today again. I want to do more important things. So this is, again, the reverse voltage here. And this is the forward voltage. Usually this is 0.7 volt, except for an LED, where this near point here is 1.8 volt or 2 volt. All the other diodes is 0.7 volt. You can remember that. So we've done this problem for an ideal diode and a practical diode, and Is there anyone that want me to do this problem again? You can put your thumbs up if you want me to do this, but it's really on the next page, and it's actually shown how to do this problem. Must I show it again? I've disabled the microphones, people, otherwise my class gets interrupted. All right, I'll quickly go. So what we have, we've got a 10-volt source. That is fine, I saw. It's a 10-volt source, and it's a silicon line with a 2 kilo ohm resistor. Calculate the replacement value of R1. Remember, it's a 2 kilo ohm right now. We want to replace that value with another value. So that's why it says here, calculate the replacement value. To ensure that the diode current is 1 milliamp, so each of the following is for an ideal diode. So, for an ideal diode, what we will have there is, I wonder if I can draw here, for the ideal diode, when that is connected, let's try to draw to the battery there. So this 2 kilo ohm resistor, 2K. And so it was a 2K. But it's the wrong value and we want to replace it here. That's why it says calculate the replacement value for R1. Because the current is incorrect. So my battery plus is here, my battery minus is there. The ideal diode doesn't have a volt drop, okay? I'm putting over 10 volts over here for my battery. So I equals V over R. So in this case, 10 volt divided by 2K will give you what current? That current is 5 milliampere. Okay, so it is a wrong current. You see now, it's wrong. So it's asking you, calculate the replacement value of R to ensure that the diode current of 1 milliamp will flow. So we want a 1 milliamp current here, not 5 milliamp. Therefore, 10 volt divided by 1 milliamp gives me what value here? 10K. So if you get 1 milliamp, it's 10 volt divided by 1 milliampere, and will give me a 10K. So my resistor will change to 10K. So it's not a 2K anymore. It's now at 10K. So for this first problem, for the ideal diode, this is the answer. Remember, for an ideal diode, there's no 0.7 volt drop here. There's no volt drop over over an ideal diode. And that is why the replacement value for the resistor for that 2K must be a 10K. Right, so let's do the next one. I'm gonna put my 2K there again. I'm starting with a 2K and I can see it's wrong again because now the voltage here for the second diode, which is a practical diode. A practical diode means a normal diode that you can buy in a shop, a normal real life diode, okay, a physical diode. For a practical diode, and this is always 0.7 volts. So to get the current here is 10 volt minus 0.7 gives me 9.3 volts. So it's 9.3. My writing is a bit ugly. Divide by 2K in this case, 2000. If I divide it by 2000, I also get a current that is much bigger. Sorry guys, just give me 1 second. So therefore, that gives me also about 4.5 milliampere. Just in a class. Thank you. All right. People are trying to call me. So guys, you see, it's a wrong current. But we want 1 milliampere. To get 1 milliampere, I must divide that voltage now rather by 1 milliampere, that 1 milliampere current, divide by 0.001. So if I do that, I can see my replacement resistor will be what? You can do it yourself. It's 9,300 amps. So the answer of this is 9K3. So the second one there, it's 9K3. So I'm going to write it 9K3. Okay. The first one was a 10K, remember? Right. So the third one, a complex diode, and it's got internal resistance of 7 ohm inside it. So what you must do now for your total resistance, you must add that 7 ohm to the total value. So in this case, I will still have the same value, and my resistance will look like this. It will be like that, and in here it'll be a 7 ohm there. 7 ohm inside the diode. So therefore, I must add the 7 ohm to the 2K. So it's 2K and 7 ohm. This is still 0.7 volts. So 10 minus 0.7 volt gives me still 9.3 volt. But now to calculate the new resistance for the 2K here, remember I don't want a 2K. I got to divide 1 milliamp into that voltage. So 9.3 into 1 milliamp will again gives me 9,300 ohm. I'll get the same values here, but it's 9,300 ohm plus the 7 ohm there that sits in series with the diode, plus 7. So my replacement resistor in this case will 9307. Okay, so I hope you can see how to do this kind of problem. So my value here will be, because I must still have 1 milliamp flowing. So 9.3 divided by 1 milliamp. Sorry, it's minus 7. Minus 7, guys. I made a mistake. Minus 7. Because 9307 minus 7 is 9293 ohm. My value will be 9293 ohm. That's what my value will be. The replacement resistance for R1. So in all three cases, it's different resistance. And this type of problem, you must be able to do. Okay. I'm done with this. Let's look at the next page. Here they actually do the problems that I've done now, and you can go through that yourselves. And here is my answers for that. These are the answers for the problems I've done now. There it shows you the answers. Okay, you can fill this in multiple choice. The depletion region for a forward biased PN, we're asking that. And the depletion in a forward bias region. And guys, go and read through the text and see what happens here. People, nobody can join my lessons, and I see they're trying to join my lessons, and they can't do it because I've blocked everyone else except you guys. So they must not try. Swane DF, one of them. Right, so go through these multiple question answers and work them out. It's part of the test that you'll do in your semester test one. Right, also describe the case of a zener diode. Explain how a zener is used in a voltage regulation. I've already done that. And describe the varactor diode. You see that? So these questions just shows you what questions will be asked. So the zener diode, like I said, again, here's the circuit for it. There's your battery voltage. It's reverse biased, remember, in quadrant 3. So this is reverse bias, and in this case, it looks like a 10-volt zener. I can't see very well. So in this case, when you've got a zener diode, a 10-volt, and you've got a 20-volt battery, it's 20 volt, and a 10-volt drop over here. The rest of the voltage drop, the other 10 volt will drop over that resistor. Because 20 volt minus 10 volt equals 10 volt, will drop over that one. Now, when we have the volt drop voltage over this one, now we can calculate the total current. And that's what I'll do in the exam. I'll tell you, for instance, in this case, calculate the total current here. So the current is 10 volt, divide by that resistor, and that will be the current that will flow through the circuit. Okay. This again shows the zener diode. It's got a positive, if you put it in a forward bias, it's also 0.7 volt, but in a zener reverse bias mode here, it'll sit here, and it will, the voltage here will be the zener voltage. If it's a 5-volt zener diode, the voltage will be there where my dot is. That's about 5 volt. If it's a 9-volt zener diode, the voltage will sit here. It depends on what zener diode it is. If it's a 25-volt zener diode, it'll sit about here, the zener voltage. And you can use this zener voltage in different ones to regulate the voltage to a constant voltage. Right. Let's look at the next slide. I think I'm really going through it. I'm not going through this varactor diode. You guys can read this. I've done it already. And I've done the circuit. You can also read through that. This one as well, an LED, and how to calculate the current. Same story. You guys can calculate that too. So the next one is the 7-second LEDs. We've done through that. And that as well. I can just skip a few things here very quickly. And I'm done with these slides too. So I'm stop with that. And now let's quickly look at your tutorial, which I do, and I'll help you with some problems there. I'll just stop sharing. Let's put the tutorial on. Today's tutorial. It takes a while. Okay, it's so small that I can't see this. I have to make it a bit larger. Right. So guys, here we've got 3 problems. Can you do that and calculate for me the voltage between A and D, C and D, and between A and D is from there to D, A to D. Calculate that voltage. And who can tell us what's that voltage? What you can do, just send us a little message that we can get your answer. So what we've got a 680 ohm and a 220 ohm. And what is the voltage, for instance, between C and D? That's a normal diode, so the voltage between C and D in this case. I think what I must do is I must do it on my camera that you guys can see what I do. No, I don't have it. I think you've got your tutorials. If I remove this now, then you can't see that. But basically what we have is we've got a 680 ohm, a 220 ohm, and 0.7 volt over the diode between C and D. So to calculate the voltage, I can use the voltage divider rule. And then when I use the voltage divider rule, the voltage between A and C equals 8 volt minus 0.7 volt of the diode. So 8 minus 0.7 gives me that voltage between A and C. Now that I have that voltage over A and C, that is basically 7.3 volt. I can use the voltage divider rule. So 680 and 220 for the 2 resistors. Fine. So let me just use a pen here. So the 2 values on the voltage from A to C is 7.3. So 7.3 is the total voltage from there to there. Therefore, the voltage from A to B is 7.3 times 680. That's now the top resistor. Divided by 680 plus 220. So 700 is 900. So that will be 900 ohm. Divided by 900 ohm. So that's the formula for the voltage diode. In that case, this voltage here will be equal to 7.3 times 680 divided by 900. And I've got that voltage. The voltage over this one will be 7.2 times 220. Let me just delete this one. $220 divided by the 900 ohm, and then you have the voltage for this one here. Is that clear, guys? So let's look at the second problem. In the case of the second problem, we can see that there is now only a 680 ohm. And I want the voltage between E and F. So the voltage between E and F is equal to 9-volt battery minus the diode 0.7 volts. So 9 minus 0.7 is 8.3 volts. So over the 680 will be an 8.3 volt voltage. And let me just write it in, and then the power dissipated in a 680. 8.3 volt here. So the power dissipated is V squared over R. That's 8.3 squared divided by 680. And that gives us 0.1 watt. The power there is 0.1 watt. Okay. And then let's do the last one. The current drawn from the battery. Now the current is my battery divided by, in this case, sorry, not the battery voltage, but the voltage over the 680 divided by the 680 ohm, and that will give me that value. So it's 8.3 divided by 680. And that gives me 12 milliamp. 12 milliamp. Guys, does that make sense to you? The next question is now question 2. It's asking list indicators, readings when testing silicon nitride with a digital multimeter for the following conditions. Okay, in this case, you had to do in your practical, which you didn't do this week due to the strike. And so, by the way, I've got all my sympathy for the people in the strike, but they are not wrong. They are all right. I will even strike with them because it means you are hungry, you don't have food. I understand that. People that wants to strike, they've got big problems. I can tell you, this NSFAS is just doing it not in the right way by not giving the food. I'm not very happy myself with it. The duty strike, you couldn't do your practical, but what you must do this one, go and measure it, and you can see what happens with your diode when you measure about across it. Okay. Now compare two characteristics of each of the diode, and then discuss the processing of doping. So that is a question you must find it there in the theory. And then discuss the process of doping. What is doping? And what is a p-type semiconductor? How do we make it p-type? How do we make it n-type? Remember, we dope it with different impurities. So we can use arsenic. So when we doping means we take a piece of silicon, we take a drop of arsenic and we put it on top of it. And that arsenic will leach into the silicon material, causing that material to become conductive. In other words, a diode. That's how they make a diode. They put a little bit drop of arsenic on top of a piece of pure silicon, and they create a diode. That's what they do. So what they're talking about here in this question is, how does doping work? Guys, you guys must read that stuff. It's all there in the notes. It's on Bright Space. There's no really excuse. Go and read it there and then see what is the doping process. There's a few steps. There's like 5 or 6 steps how to do the doping really. I'm not gonna go into this. And then now the next question. With the aid of the diagram, describe forward bias. Remember, I've explained to you what's forward bias. Forward bias is when this diode is put in quadrant 1 on your graph. In other words, the positive of the battery goes to the positive of the diode. And the negative of the battery goes to the cathode here. Sorry, let me just scroll on. Talking here in the air. My battery plus will be there and the minus will be there. So the positive is the anode, it goes to the plus of the battery and the negative goes there. In this direction of the battery, puts this diode in quadrant 1. That's quadrant 1. Do you see that one? The forward bias. That's this answers this question really, this graph. You can also in exam draw me a graph and show me meaning this quadrant 1 and how it looks. Look. And it will be 0.7 volt. Also write 0.7 there. Forward biasing is always 0.7 volts. Only LEDs, they are 1.8 volts. Yeah. But all other normal diodes is 0.7. So I expect you to know that. Right. So that brings us to this circuit here. And it's too small for me. So what I do, I go to my PDF file now on my computer. So give me a second. So on that circuit, we can see what we must calculate is I1. I1 is the current through the resistor, né? So can you guys see that there's 0.2 volts over the diode, D2? And that 0.2 volts is over that 3K3. So what we have there is be with you in a minute. And then I'll help you to analyze this one. Right, I'm done. I've got my circuit. I'm going to now redraw the circuit from that because I cannot see this one. It's only for you. You can see it, but I can't see it. So what we have here is on this diode, we've got 0.2 volts. I'm going to write 0.2 volt. Sorry, 0.7. What am I writing, guys? 0.7 volts. The 0.7 volt over the diode will fall over that resistor. So what will be the current through that one? Guys, you can give me the answer. You can chat. You say chat and then you can type the answer there. No one is typing. Then 0.7 divided by 3K3 And that gives me 0.2 milliampere. Okay. 0.2 milliampere, yeah. Okay, so they are also asking what is the current through ID2. We know this is 0.2 volt over ID2. 0.7 volt. What am I saying? 0.7 over D2. And we know there's 0.7 over D1. So it's the total volt drop will be 1.4 volt. So calculate the current there. I will have to say that the total voltage over the 5K6 will be 20 volt minus 0.7 minus 0.7. All right. So it's 18.6 volts. So the voltage over here is 18.6 volts. 18.6. How do I get 1.7? This voltage plus this voltage plus this voltage equals 20. Kirchhoff voltage law, ne? 20 minus 0.7 minus this 0.7 gives me 18.6 volt. And that's why I'm putting this value. And the current that will flow there is 18.6 divided by 5K6. 18.6 divided by 4,600. And it is 3.3 milliamp. So my current here will be 3.3 milliampere. And then the question asks, what is I1? We've got it. ID2, we've got it. And I2. So this total current here, the total current flowing into the battery again, this one, the total current will be this total current flowing here will be this current 18.6. Oh, sorry, 3.3 milliampere plus 0.2 milliampere. That will be my total current. Someone's asking, how did we get 11? What is that 11? I1. Sorry, I1. Okay. Remember, I1 was the current through the 3K3 ohm. I1 was this current, people, this current. How do you get this current? This current, I, is V over R. What's the voltage over that resistor? It's 0.7 volt over this diode. So that current is 0.7. No, pen, not lasers. 0.7 volt divided by this 3K3. Very ugly, that 3. So let me do it again. 0.7 divided by 3,300. So it's 0.21 milliampere. You got it. 0.2. 1 if you want to, for more accuracy. 0.2 is not very accurate. So that's how we got that current. And now we got this current here. We set that voltage minus 0.7 minus 0.7 is 18.6 volt. And the current through that one is 8.6 volt divide by that resistance. And that is where we get the 3.3 milliampere. But the total current here is actually that current plus that current. You must add the two currents together to get the total current. Okay, he says, I don't understand what's going on in this problem. I've explained it now again. I do not know why you cannot follow what I'm saying. I don't understand you. I'm so sorry. Maybe you must read the notes again and so on to find out how this problem works. I don't know. If there's still a problem, does that answer you? Just type me a message, guys. Remember, I've switched the mics off so that the people can't disrupt our classes. We don't want to struggle with that. So that's why I'm doing that, so that we can at least. Okay, good. He says he's got it, he understands it, very good. Second time always works, né? I must always explain 2 times, I think. 1 time is not good enough. All right, so let's see the last one. Last one. I can't read there. Very, very small. So the last question says, what are the majority carriers in intrinsic material? It's in my notes there. The first slide, it's all there. We call about minority carriers. So remember, there's a P in the N region in a diode, a positive and a negative region. And remember, the positive region have got a lot more holes. Holes is the positive parts, sort of positive ions. So the majority carriers in the P region is the holes. The majority carriers in the N region, that will be the electrons. Go and read those notes. So when the diode sits like there, this is your anode, and this is your cathode. And there is this, the barrier. Remember, this is the band gap. We are talking about the band gap barrier. Okay, so this is the positive and this is the negative one. Right. So there are a lot of things that here are the electrons sitting here. You can write a E or a minus if you want. They are sitting, the majority electrons sit in the inner region. The majority holes sit here. They are the pluses or the positive ions, sort of, so to speak. They are sitting there. We also call them holes. Holes and electrons. So all the electrons ran away from here and they then to go and sit on this side. It's like a capacitor, guys, where you charge a capacitor, all the positives ions sit here and the negative electrons go and collect on this side. And therefore, the majority carriers here is electrons, the majority carriers here is holes. You got it. And then materials are classified into 3 categories: insulators, conductors, semi. You must describe it and tell us, compare conductors to semiconductors. What are conductors, what are semiconductors, and what is the energy levels in them? But the band gap's got energy levels. We've told you, when the band gap is very narrow, the energy is very small. The energy is small. However, when that band gap is wider, like this, when we apply voltage over it, it's much wider, the energy will go up and the energy will be bigger. Go and read my notes on this stuff so that you can educate yourself. What is a conductor and what is a semiconductor? So a semiconductor conducts also, but only when you go above a certain voltage. For diodes, that voltage is about 0.7 volts. if you stay below 0.7, the semiconductor doesn't really conduct. It only conducts like above 0.7 volt. So that the band gap must be big enough for conduction to take place, to make it a conductor. So it's not always a good conductor, it's a semiconductor. That's why we've got that funny word, semiconductor. An isolator is like a piece of paper. We have a piece of paper here, and you put a wire there, and you solder another wire to that side. Maybe you can get paper solder, I don't know what. I call it Prit. You think current will flow through this paper? Guys, you can try as hard as you can. The current will never go. You can't shock someone with paper. If you want to shock someone, take a capacitor. That one. You put a whole high voltage there of 60 volts. And it will shock someone, but not paper. Paper doesn't work. Not good enough. Not a conductor, so this is a non-conductor. This is a semiconductor, and a conductor is like maybe iron or copper. All right, guys, I'm really done with this thing. Can I switch the mics on if you have any questions? I'm telling you, it's a long story to switch the mic on or off. Right, there you are. You can talk to me if you want to. All right, guys, now it's safe to talk. Any questions on this? There are questions on this tutorial paper. Anything you want to ask?
Hey, some people transferred, Baba.
Yes, sir. Can you please ask?
Yes.
So based on the previous quiz, some of the questions were on Unit 2, and we were not yet familiar with them, so we didn't score good marks. So I'm not sure how we're gonna work on the results.
Explain that to me. You don't have Unit 2 or what? Don't you have it?
So we only learned some of the problems that were